Hey, how's it going? Alright, haven't made one of these videos in a while. Let's see if I remember how to do everything. So looking here, this is the quiz review that I made for you guys. The first question is about a sliding ladder. And I found this graphic to sort of help you visualize what's going on. But you can see the ladder starts up here at like 10 and the bottom starts sliding out pretty quickly at first. You see the bottom is moving fast and the top is not moving that fast, right? Top comes down slow, but soon as it gets further down, the top now is coming down really quickly while the bottom is skidding out rather slowly. So you've got those related rates going on. This sort of helps you see it, I hope. The other thing that's a little harder to notice, but that red line is not changing its length. So this vertical leg of the right triangle is getting smaller, 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 while this horizontal leg is getting bigger, bigger, bigger. But the hypotenuse is remaining constant, a constant length the whole time. So that's what's happening there. Now what? I don't know. I think I just throw that in the trash, basically. I don't want that anymore. So now let's read the question and attack it the way it actually is. So I would want to draw the floor or the ground, whatever it is. This feels weird. And then I would need a building. Oh, that's not a right angle. Hopefully you guys can handle it. All right, and then there's a ladder coming down, 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 down. However you want to angle it. But here comes a ladder. Ooh, my drawing skills are not so good anymore. All right, but there you go. So what do we know? It says the ladder's 20 feet. Fine. So there's that dimension. If the bottom of the ladder slides away from the building horizontally at a rate of 4 feet per second, that means this dimension, as we slip along the floor, that's 4 feet per second. And no, it's not negative. I'm going that away, and that distance is getting bigger as I go, so it's positive 4. It says, how fast is the ladder sliding down the building? So how fast we're sliding down, that's the thing we're trying to solve for, is that rate of change there. And it says when the top of the ladder is 8 feet from the ground. So when this dimension is 8 feet, we want to find that rate of change. All right, so first of all, we're missing a dimension. We don't have this dimension here along the ground. So for these kinds of problems, we do want all of the dimensions. And why do we want them all? Well, we want them all because think about the equation that relates all of these things. It's the Pythagorean theorem. So a squared plus b squared equals c squared. So if I leave all of those things as variables, don't substitute anything in just yet, and then do the derivative, you get 2a dA dt plus 2b dB dt equals 2c dC dt. If we do all that, then you see that no variable actually cancels out. I still need the length of A, the length of B, the length of C, the rate of change of A, rate of change of B, rate of change of C. So for these kinds of right triangle problems, I can't be missing anything. So I do need to find this measurement here. Luckily, that's pretty easy to do. You just use the formula that you just wrote, which is the Pythagorean theorem. So I'm going to let A be what I imagine is that shorter of the two legs. It's probably longer actually, but whatever. But I'll plug that in. We'll go 8 squared plus. If that's going to be my A, then this is B. So now we go B squared. And of course the hypotenuse has to be C, so that's 20. So we get a 64 plus a B squared. Forgive me when that happens with my 4s, by the way. That's meant to be a 4. Sometimes the line just gets wonky. But this is going to equal 400. So I'll subtract 64 from both sides to get a b squared that equals 336. Then I'll take the square root and I'll get the square root of 336. And you know that you may not reach for your calculator and just give me a decimal. You got to actually keep this radical, and you should keep it in reduced form too. So if you can't immediately tell what factors of 336 are perfect squares, then you could build a prime factorization tree. Just take the 336. I'm going way the heck up here in this corner. But just start breaking that down. It's pretty obviously divisible by 3. You get 1, 1, 2. And that's prime. So that's the end of the line. Then the 1, 1, 12 is, I don't know, divisible by 2, I can see. So we get 56. A 56 is a 7 and an 8. So there's a factor of 7 and a factor of 8. The 8 is a 2 and a 4. And the 4 is a 2 and a 2. All right, what was the point of all that, you might wonder? Well, that tells me that 336 has a factor of 4, but then it has another factor of 4 from these two 2's, and a 4 and a 4 is a 16. So by looking at all those prime factors, I can figure out that 336 is divisible by 16, and the remaining factors, the 3 and the 7, that tells me what else is there. It's 21. So 336 is 16 times 21, which means I can break that radical down to 4 root 21. And now I have the third side of my triangle expressed cleanly as a radical. So 4 root 21 is going to be the value of b. And this is good news because now I have everything I need and I can substitute in. So into my derivative, I've defined a to be this side here, that's 8. So it's going to be the 2 times the 8. And then dA dt is the quantity we're trying to solve for. We were trying to find the rate at which the ladder was slipping down the wall. So dA dt is our one variable. Everything else is getting substituted in for. So now we've got a 2. We've got our value of b, which is the 4 root 21. And dB dt was the rate we were slipping along the floor. That was given to us as 4. Then actually over here, nothing matters because the rate of change of c is 0. The ladder is not changing. So this whole side would actually go to 0, which actually kind of harkens back to something I said in class, today and the day before today and some other days. But I told you to always be thinking about which variables here are truly variables. And c is not a variable because as this ladder slips, c isn't changing. This c is a 20 all day long. And it is fine for me to substitute in constants even before I differentiate. And you can kind of see why here now. It's because if I differentiate this 20, I get 0. But even if I left it as a variable and got 2c dc dt, well, the dc dt would be 0 because it's the rate of change of a constant. And then whatever the value of c is would be irrelevant because 0 times anything makes 0 anyway. So I don't know, maybe it would have been a little more efficient if I just let the c be 20, but the a and b would have to stay variables because a for sure is changing as the ladder slips, and b is also changing as the ladder slips. So a and b must remain variables when I differentiate, but honestly the c did not need to be a variable because it wasn't a variable, it was a constant. By the way this situation is defined, it's a constant, it's not actually changing. Alright, but however you get there, I hope we all agree that where we are is where we're supposed to be. I'm looking at a 16 times dA dt. And I'm adding to that, let's see, 4 times 4 is 16. 16 doubled is 32 root 21. And that equals 0. So to solve for dA dt, I'll just subtract the 32 root 21. So I now have negative 32 root 21. And to isolate dA dt, I'll divide by 16. So when I divide by 16, I get this big expression that pretty obviously I can reduce here to get a final answer of a dA dt that is equal to negative 2 root 21, which of course is approximately, I don't have a calculator handy, so give me a minute and I'll find one. Okay, I found a calculator. And so I can now do 2 times the square root of 21 to get my decimal approximation. And according to this, 2 root 21 is 9.165. So turn that calculator off now. 9.165. Turn off. All right. And I know it's negative. It's negative 9.165. So there we go. All right, and I know that I need my units. And let's see, they already gave me the units for the rate at which we were slipping along the floor, so it certainly makes sense that the rate that we're slipping down the wall will be the exact same units, which is feet per second. there you go. There's one whole Pythagorean theorem style problem, and hopefully that made some good sense. If it didn't make sense, then come talk to me about it. All right, next question on the quiz review that I posted that you can find on Canvas is this one. It's about baseball. And I had a little graphic for this too that I forgot to get, so let me go get that. Okay, so here's a little baseball diamond. Not everybody needs to care about baseball. In fact, whoever made this doesn't really care about baseball because home plate's backwards. That flat edge is supposed to be forward, so haha, nice try, nerds. Anyway, first base is over here, so if you're at bat and you hit the ball, you run to first base first, then second, then third, then home. If you read the question, which I'm sure you should have, then there's a runner who's already on second base and he's running toward third, just like you see this little pink guy here is animated to do. So as he runs toward third, we could measure his distance from home, and we see that that distance for sure is shrinking, shrinking, shrinking. So now what this graphic did get right is that the distance between bases is supposed to be 90 feet. So the problem that I gave you guys, I don't think it got it wrong. I think they're saying 80 feet. It's probably like a little league baseball field. Could be 80 feet, a smaller field. Or maybe a softball field is smaller. I don't know. Anyway, it's 80. We're going to definitely use the 80. But notice right here is sort of where our problem would stop, because our problem wants the runner to be 60 feet away from reaching third. So that would give us this dimension at 60. And obviously that would mean that the distance we care about is right there, that moment in time. So that distance. But this problem is pretty similar to the last problem. If you stop and think about it, we're still looking at a right triangle, because a baseball diamond, it's not really a diamond, it's just a square that somebody turned 45 degrees. So we've got ourselves a right triangle, and again, we know these two legs are 60 and 80. They probably made the side lengths 80 here to make your life easier, because you may remember that 3, 4, 5 was certainly one of our Pythagorean triples, and 3, 4, 5 doubled is 6, 8, 10. And so if I then multiply that by a factor of 10, instead of 6, 8, 10, I get 60, 80, and 100. And we already talked about how we are going to need all three lengths of the sides of our triangle. Probably. There's one length here we didn't actually need. The one length we didn't really need was the 80. Because that side, as you notice, as this pink man is running, that's the one side that's not changing. That side is constantly 80. But this side here is shrinking, shrinking, shrinking as this person runs. And obviously the distance between the person and home is shrinking, shrinking, shrinking as well. So actually the only reason I needed the 80 was so that I could figure out the hypotenuse. But as far as all the setup goes here, hopefully you guys are with me. I guess I'll leave this here, even though watching that man run is kind of distracting. But let's set up the equation. We know it's just the Pythagorean theorem again. A squared plus b squared equals c squared. And again, we could go ahead and differentiate that now as is, or we could take note of the fact that I'm going to let this be A. So then this is B and this is C. In this problem, it's actually the length of B that's being held constant. So if I wanted to substitute in for B, I could. That's going to be 80 squared, which means when I differentiate that whole thing, I'll just go to 0. So I get 2A d80t. If you want to differentiate this for real, then you would get 2b db dt, but I'd like to think at this point we know that whole term is going to go to 0 no matter what we do. And then here we get 2c d c dt. Alright, and I haven't even fully read this problem, but I know that I got a 2. I need the length of A. A was given to us to be 60 because that's the snapshot moment in time where they want to freeze us. So boom, this is the moment we care about. And at that moment, A is 60. So that's 60. The rate of change of A would be the speed the player's running. So if we read, it says he's running at a speed of 28. But be careful, again, because he's running in a direction that's causing the length of A to shrink, we have to remember to let that rate of change be negative. This is negative 28. And then the 0 is 0. Who cares? This is 2. C is the length of our hypotenuse, which again, at the snapshot moment in time, when we're 60 feet away over here, this thing will be 100. and dc dt is what we're trying to solve for. So we've done it again. We've written an equation, differentiated it, and we've plugged in for everything except for the thing that we're trying to solve for, which is great. So what does all that stuff multiply out to? Let's bring my calculator back. Boop. And then as a side benefit, that covers up the man that keeps running by and distracting me. Now that is messing up my calculator. Okay, give me a second to fix that. Okay, so this is better. And I just needed my calculator so I could do not the 60 times the 2, that's obviously 120. Then I'll multiply that by 28, and that's giving me 3360. So this is negative 3360, and that's equal to 200 times dc dt. So I just divide, and we get close to our final answer. We get negative 3360 divided by 200, which I can certainly start to reduce on my own. Those are both divisible by 10, so I can kill those. If you remember, we actually saw 336 a second ago, and it was divisible by 4. But I don't remember what that left, so we'll just use our calculator. And I don't mind showing you one more time how to actually do this. If you're not comfortable reducing your fractions, remember that from the get-go you can just type in 3360, divide that by 200, go ahead and say enter to get to your, oh, well that should be a pretty easy one, but hit enter, get your decimal, and then remember you can always hit math, which is right here, and you choose the convert to fraction. So there's really no excuse not to reduce my fractions for me, but I would be expecting you to give negative 84/5, and then also to mention, yeah, and you don't have to say it's approximately equal to, because it's exactly equal to 16.8. And we do need our units, but we were already given one rate of change, which was feet per second, so this one's also going to be feet per second, and that's dc dt. So this question was very similar to the last one. These are both right triangle problems, but that's good. You saw 2 examples now, which is lovely. Let's move on. So the next one, let me get this calculator out of my face. So this next problem is about a melting snowball. We've talked about spheres before, but let's do it again. So for this one, I couldn't find an actual animated graphic of a snowball melting. Maybe if you guys can find one, you can let me know. Let me know down in the comments. Isn't that what you kids say in your YouTube videos? Here's my snowball. Not the best sphere. In fact, I hate it. I'm starting over. That's the worst sphere I've ever drawn. Alright, I'm going to make it actually spherical. Oh, that's not so good. Boink. Alright, so there's a perfect circle. To make it look more like a sphere, we'll have an equator run around it. That'll make it look nice in 3D for us. So boink and boink. Alright, and what do we know? We know that the snowball has an outer layer of ice and it melts, and as it melts we are assuming that it stays spherical in shape, which may not be true to life, but that's okay. But it says the volume is decreasing at a rate of 2 cubic centimeters per minute, which means dV dt is negative 2 cubic centimeters per minute. It says how fast is the radius changing when the diameter of the snowball is 10. So if the diameter is 10, I don't really care about that. I would just want to know that that means that the radius is 5. So I don't really need this number anymore. It says how fast is the radius changing. That means we're after dV, dr dt, of course. But that should be it. These should be basically the only variables at play here, because the formula for volume of a sphere is 4/3 pi r cubed. So there's literally only a v and an r. When I differentiate, the v goes away because the derivative of v is 1. We get dV dt, which is a measurement that we have. Then if we, oh, did I write squared? I hope I said cubed at least. Of course it's 4/3 pi r cubed. But to differentiate now, I'll multiply by 3, and the 3's cancel, so I get 4 pi. Then of course I'll drop the power on r down to 2, and then I'll chain rule out a dr dt factor. But there's my whole derivative, which only has 4 variables. There's the dv dt, which we already know to be 2, or negative 2, because we're melting. 4 is 4, pi is pi. The radius at the moment that we care about, we know to be 5. And then the only other variable is the one we're trying to solve for anyway, dr dt. It says how fast is the radius changing. That means we're solving for dr dt. All right, so this is a negative 2 that equals 20 pi times dr dt. So to solve for dr dt, just divide. And 2 over 20 pi would end up being 1 over 10 pi. And that's dr dt. And in terms of the rate of change, well, the volume was changing by 2 cubic centimeters per minute, but we're now talking about the rate of change of the radius, and the radius is only measured in plain old centimeters. So make sure your rate of change is plain old centimeters per second. Don't say it's cubic centimeters, that won't be right. All right, and then I do need my decimal to go with this. So, yoink. I'll type in my answer. And again, just be super careful that you don't kind of absentmindedly say 1 over 10 pi without using parentheses, because that's not going to be the right answer. We need to type 1 over and then put the 10 pi in parentheses so that we're dividing 1 by both the 10 and the pi. We get a completely different answer here. We get 0.0318. Centimeters per second equals dr dt. And of course, don't forget, that's negative, because as the snowball melts, the radius is getting smaller and smaller. So there you go. There's another practice problem. This one about a sphere. Okay, next. A brush fire. Okay, so imagine a green field. Green field. Oh, that's weird. But that's all grass. So grass, grass, grass. But then imagine something sparks a brush fire, probably a bolt of lightning or something. But if a bolt of lightning struck right there, then assuming there wasn't wind sort of blowing the fire in one direction, then it would sort of grow out in all directions, getting bigger, bigger, bigger. The inside should look more burned, but there you go. This is sort of what you should be imagining, is just there's this fire that's growing, 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 outward, outward, getting bigger and bigger in area. And probably you could have pictured that anyway without my sort of not that good animation anyway. But let's see what we know. If we're talking about area, and if we're talking about area of a circle, then the formula there would be area equals pi r squared. Which certainly implies that the only variables here for me to worry about are area and the rate of change of the area, and the radius and the rate of change of the radius. And I haven't even read the question, so let's read it. It says a fire starts in an open field and spreads in the shape of a circle. The radius of the circle is increasing at a rate of 6 feet per minute. So that's obviously dr dt. And it's obviously positive because they literally said increasing at a rate of, so that's positive. It says find the rate at which the area of the fire is increasing. That means dA dt is going to be the ultimate answer to the question when we're done. It says find that thing when the radius is 150 feet. So this is 150 feet. So again, you might notice that we currently don't know the area. We're sort of left to wonder what's the area. And there's two things you could do here. You could just bite the bullet and find the area since you've got the radius, but I think we know that we're not going to end up needing it anyway, because as soon as we differentiate a, we just get 1 dA dt. And we see that the a doesn't even make it into the derivative equation, which means the area here is irrelevant. We just don't even need to find it. As I differentiate this side, the right-hand side, I'll multiply by 2 to get 2 times pi. The power on r goes down by 1, and I get a factor of dr dt. But this is it. I mean, there's the derivative for our expanding circle, so just enter all the stuff you know. dA dt is what we're solving for. And 2 is 2 and pi is pi. But at the moment we're examining the radius is 150. I can substitute that in. And at the moment we are examining, the radius is changing at a rate of 6 feet per minute, so that's a 6. So apparently dA dt is nothing more than, let's see, 2 150s are 300, so times 6 is 1800 times pi. And since we're talking about area in feet, this area must be square feet, and the unit of time we're using is minute, so the rate of change of the area must be square feet per minute. So there's your exact answer. And I am still hoping that you guys will give me your decimal approximations too. So for our decimal approximation, yoink, we want 1800 pi. So I'm getting 5,654 point 867 square feet per minute. And there's another one down. Let's keep going. All right, so this mobile spotlight problem. So this one was meant to be a riff on the street light problems that we've been doing. I wanted to change it at least a little bit. So I decided, instead of having a person walking toward the light, what if we put the light on wheels and had the wheels bring the light towards the person? And I needed that person not to move, so I changed it to a deer, because deer don't move, right? Hence the saying, like a deer in headlights. So okay, there you go. So again, if you can imagine this, imagine if the light were over here and it's coming sort of closer and closer and closer and closer to the deer. So in this position right here, it would cast a shadow that goes way, way out to here, which is pretty true, because notice I made the height of the spotlight 60 inches and the deer was 52, so there's only a couple inches difference between them. So that angle between them would be a pretty steep angle, which would cause the shadow to go out quite far. But if we brought the trolley in even closer to here, then suddenly now that line is even steeper, and it creates a shadow that's smaller. So if I have the light come out, hit the tip of his antler, and go here, then we can see that as this trolley brings the spotlight closer and closer and closer to the deer, his shadow is getting smaller, smaller, smaller. All right. Again, don't draw too many triangles, you'll confuse yourself. But the two triangles at play here are the one defined by the height of the spotlight, and then the distance all the way out to the end of the shadow, and then the hypotenuse being the shadow itself. And then the second triangle, the one that's similar to the first triangle, is the one determined by the deer's antler. And then I come straight down and I run across the floor and I run up along this light beam. But those two triangles, the green one and the lavender colored one, we know those guys are similar, which is going to be key to this problem. So for these problems, the way we've broken this down was to label variables like this, where the height of the first triangle we called capital H, then the height of the person, or in this case the deer, we called lowercase h. Then we broke these dimensions down, and I think we called the first dimension here A, the second dimension we let be B, which comes over to here, and then the total length, and I realize I'm going to go behind my own face over here, but that's fine. But the total length there was C. These were the only measurements we ended up needing to care about for problems like this. So let's go from here. Can I grab this whole thing and move it? Sort of. Oh, geez. Okay, let me stick this in a corner over here. All right, so what do we know? We know that because these triangles are similar, we would want to let this vertical edge of the green correspond to the vertical edge of the lavender, and that's going to set up a ratio for us. Then we also want the horizontal edge of the green to correspond with the horizontal edge of the lavender. But basically we're going to grab those dimensions and make a proportion out of them. And a proportion is when some fraction is set equal to some other fraction. So looking at the pink, we know that we can say that capital H divided by a little h, that's going to be our first ratio. And our second ratio would be, technically it would be C divided by B, but I think we learned that we don't really want to introduce C as a variable if we can help it. We would be more interested in A as a variable, and the answer to that, why would we be more interested in A, is because, well, if we actually read the question, it says, at what rate is the length of the deer's shadow changing when the spotlight is 4 feet away? By the way, everything else is in inches, right? So 4 feet is not a number we want to use. We'd want to convert that to inches and call it 48 inches. Do I intend to throw unit changes at you on the quiz? I don't think so. If you guys see something in feet and then something else in inches, if I were you, I'd just raise my hand and ask me if I really meant for that to be the case and for you to have to convert it, because I don't think I do. Certainly wouldn't have you converting feet to miles or like yards into something else. I know some of these conversion factors are easy, but I'd rather not mess with it. You guys should only have calculus as your headache, not conversion factors. So where are we? Anyway, so that dimension is A. It turns out not really mattering, but it does kind of give you a hint that maybe we're more concerned with A and B than we are with B and C. So I'm going to break this down, a lot of it down actually. This guy's going to want to be A plus B rather than C. And this is also the problem where we really wanted to substitute in before differentiating if possible. But again, the only thing you're allowed to substitute in for are the quantities that are actually constant. And again, if you imagine this moving trolley thing, then capital H is not changing. As this trolley moves, that spotlight is staying at the exact same height the whole time. So since H is constant, we can substitute in for H even before we take the derivative. And we were given that the height is 60 inches above the ground, so in goes a 60. Now the deer is just standing there standing still, so of course its height is not changing. Little h is not changing, and that was given to be 52. So there's our first ratio. Then for the A and the B, well, this 48 is changing. As this trolley moves back and forth, that dimension changes. And B changes too, because as we go back and forth, the length of our shadow is actually changing. So even though the deer's not moving, remember, if we snuck this trolley in a little further, then the line goes more like this, and the value for B shrinks. So B has to remain a variable, which means I can't mess with either of these. This has to stay an A plus a B, and this has to stay a B. Those are going to be our variables. So now I want to differentiate, but I would cross multiply first if I was you. So I'll cross multiply to get a 60B. That equals 52A plus 52B. And hopefully you notice right away that you can just subtract 52B from both sides to combine those terms. So now you just have an 8B. That equals 52A. And it's from this point that you would go ahead and just do the derivative now. So we'll do ddt applied to both sides of this equation. And of course that gives us 8 dBdt's that are equal to 52 dAdt's. And it's at this point we notice we don't care about the measurement of A. We don't even care about the measurement of B, because when we differentiated, B fell away, even A fell away, And the only thing that matters here are the rates of change, which is fine by me. So I'm going to kind of work over to here. But we've got 8 times dB dt. Now dB dt is the answer to the question, right? Because it says at what rate is the length of the deer's shadow changing? And surely that's what B is. It's the shadow of this deer. Can I draw? I don't think I want to draw a deer's shadow, so I won't bother. But that is going to be the expression that remains our variable, which must mean that I do know the value of dA dt, and I do. dA dt is the rate at which this dimension is shrinking. So that would be the rate that the trolley is moving, which was given in the very first sentence. It's 6 inches per second. And since we're going toward the deer and this measurement is getting smaller, you got to remember to make that a -6. But that's it. From here, I would divide by 8 and I get a dB dt. That's equal to whatever 52 times 6 divided by 8 is. I'm not going to get too fancy here trying to do it. I'll just let my calculator do it. But maybe, just to impress somebody, you guys do get that 52 is just a 2 times a 26, right? But 26 is just a 2 times a 13. But 6 is just a 2 times a 3. And this is all negative, right? So guess what just happened? I just found in a 52 times 6 a factor of 2 and a 2 and a 2, and 2 times 2 times 2 is 8, so I can cancel my 8, and I see that my final answer here is -39. Just a little trick for you if you find yourself without a calculator, but you guys never find yourselves without calculators, so if you just wanted to do this out, what happened to my calculator? If you just want to do it out, then just do it out. So 52 times 6 equals that number, which divided by 8 is 39. But don't forget it's negative, of course. I never include the negatives in my calculations in the calculator, but then I have to actually remember to include it as part of my answer. But this one came out exactly. There's no decimal approximation for you to give. You just give your answer as 39. I do need my units though, and what would they be? Well, everything in this problem was inches, and we were moving in terms of seconds, so it must be -39 inches per second. And that's it. So again, that means that as the trolley is coming in at a rate of change of 6 inches per second, this shadow is decreasing at a rate of 39 inches per second. And if you think that's fast compared to this, at least, well, you're right. But remember that we decided the shadow was starting out very, very big. So it's not that weird that at first it's decreasing quite rapidly from its very large size. As we got a little closer to the deer, it would be shrinking not quite as fast. No, that's not true. It's shrinking at a constant rate. So it's shrinking at that rate all the time, which just, it's not that shocking. I'm going to move on. This one. All right, so this one is just about a rectangle. I'm throwing this in. I don't know if we've super talked about rectangles, but the formula is simple enough, and I think you guys should be able to handle it. So, although if you're here watching the video, maybe that means you couldn't handle it. We'll find out. It says a screensaver displays the outline of a 3 centimeter by 2 centimeter rectangle. Okay, I can draw a rectangle. So don't draw this rectangle. That rectangle looks like a square. You want one that's as close to 3 by 2 as possible. So I don't know what that looks like exactly, but maybe something like that. You want 3 unit lengths here and 2 unit lengths here. That looks fine to me. So what they're saying now is this thing now expands, and it expands in such a way that the proportions of the rectangle never change. So that means it's not like it's just growing like this. Burp, burp. If it grew like that, the proportions are changing. It's growing like this. Burp. So as the lengths grow, the width is growing also, but not at the same rate. If they grew at the same rate, the proportions would kind of go out of whack. So these are growing at 2 different rates. This longer length has to grow a little faster to keep up with the growth of the other one. But whatever, you guys probably get the concept at this point, so I'll just be quiet and we'll do our work, and here goes. We know that the formula for the area of a rectangle is just area equals length times width. And I wonder if we can get away with doing this sort of the easy way. What do we got? We've got an A, which means there must be a dA dt. We've got an L, which means there's probably a dL dt. And we've got a W, so there must be a dW dt. All right, so is any of this true? No, we wouldn't need A, because if we differentiated A, we would just get dA dt. So A for sure is in a number that we weren't given, but that we don't need to find, although it's quite easy to find it, but we don't need it, so don't waste time. L, did they give us L? It says, how fast is the area of the rectangle increasing when its dimensions are 12 by 8? So who's supposed to be the bigger dimension? I guess I haven't defined it yet, but let's say if we let this dimension be length and this dimension be width, then length is the greater dimension, so my length would be the 12 and my width would be the 8. And it says here that the rectangle is expanding in such a way that the 2 centimeter side is expanding at a rate of 4. 2 is the smaller one, so 2 is the W, and it's expanding at a rate of 2. In such a way that the 2 centimeter side is expanding at a rate of 4. 4. All right, so looking at this, I'm missing something because what I'm solving for is dA dt. So we don't have the proper rate of change for dL dt to ensure that these sides stay in proportion. So this problem is similar to the cone problem that we did in class today, or depending on when you're watching this video, we did it in class on Tuesday. But we actually had to replace one of our variables with an expression in terms of the other. That's where this 3 by 2 thing kicks in. So we know that if this rectangle were allowed to grow, we would get a new rectangle that was similar to the original rectangle, which means if I took my length and divided it by my width, that ratio will always remain constant. And by the way, that ratio is just literally 3 to 2. Okay, so the length divided by width will always equal 3 over 2, which means I can cross multiply here to get a 2L that equals a 3W. And since I don't have information about L, L is the guy that I want to replace out of my equation. So I'd want to solve for L by dividing by 2. And we find that L is equal to 3/2 of whatever W is, which allows me to come up here and replace L with just 3/2 of W, which of course times W gives me the equation A equals just 3/2 times W squared. Now the only variables I need to care about are A and W, which means length can just be a distant memory. We know that we don't need the area. We've got W and dW dt, and we want to find it for dA dt, so we're good now. We are good to go. So we can differentiate this equation to get a dA dt. That is equal to, let's see, multiply by 2, 2's cancel, you get 3W to the 1, and then you chain rule a dW dt. And at this point we're just substituting. dA dt is what we eventually want to solve for. 3 stays 3. W we're substituting in. W is worth 8 at the moment in time that we care about, so in goes an 8. And we were told that the rate of change of W was that it was increasing at a rate of 4 units per second, so in goes 4. But that's it. This was a pretty simple one. You literally just multiply that stuff out and you get your final answer of, let's see, 3 times 4 is 12, and 12 times 8 is 96. If we're trying to do this in our heads, 96. So what are my units? Well, my lengths were in centimeters, but this is an area, so this must be square centimeters. And my width was changing at a rate of 4 centimeters per second, so my unit of time must be seconds. And so my rate of change is 96 square centimeters per second. And that's your 6th problem. And I think this is pretty decent coverage for what the quiz will look like. I'll give you something easy, kind of like a rectangle. What you haven't seen on here was a cube, but we talked about a cube before. I suppose if I wanted to, instead of a cube, I could give you a rectangular prism, maybe something more like the shape of a box of cereal, where none of the dimensions are actually equal. So the cube's a little easier because we said you could let this side be S, and then that would be S, and that would be S, and your volume would just be side cubed. But if I gave you a box of cereal, then you might have sort of a medium length, a short width, and your greatest dimension is your height, and they're all different, and your volume would be length times width times height. And this would be pretty bad if I did that to you, because you'd actually have a three-way product going on. I don't know if you guys know how to do product rule with three different things. But yeah, so that kind of implies I wouldn't do that to you. But the other thing I won't do to you definitely won't be cones, because we said I wouldn't. And I won't do cylinders either. Even though cylinders aren't so bad, we won't do those. And we've seen everything else. What else did we just see? We saw a couple different right triangle problems. We saw one where the hypotenuse was constant, because we're talking about the ladder, so dc dt was 0. We saw one where one of the legs of the right triangle was held constant. So in this case, db dt was 0. What we didn't see was a right triangle problem similar to the one that we already had our small little warm-up about. Where Mr. F was moving west along a certain street and Mrs. F was moving north along a certain street, which created a right triangle. In that problem, none of the rates of change were 0. All three dimensions were changing at the same time, which is no big deal. It just means you differentiate and you would have the 2b db dt term here, but you would have both of those rates of change. You'd be solving for the last rate. It would be fine. All right, we did melting snowball. So the only thing we didn't do, I guess, is talk about surface area. If we were talking about a sphere, surface area would be 4 pi r squared. But honestly, I probably just won't ask about it since it wasn't here. We did the brush fryer problem, which was just a circle. Now this problem was about area, but I could easily ask you about circumference. Circumference is 2 pi r, and you just go from there. And then we did the spotlight problem, and we did the screensaver problem. So the spotlight problem was a lot like the lamppost problems, where we had to use similarity. And the screensaver one was a little different. It was about a rectangle. But this video is long enough, and I'm rambling here. If you haven't already shut me off, then good for you. But go ahead and shut me off. That's it. Quiz Friday. Hopefully you do great. See you tomorrow. I hope you don't watch this tonight. You got the SATs. Go to bed. Watch this tomorrow. Watch this Thursday. And you'll be ready for Friday. All right. Good night.